Okay, so this is lesson 6.4, logarithmic functions. Should be pretty much a review for you of stuff that you did in pre-calculus. So hopefully this lesson won't be too long for you. This slide just tells us everything that we're going to get to do today. It's going to be wonderful. You're going to love it. This one is all our formal definitions about logarithms, but we're going to go straight to the examples, and I'm going to teach with the examples. Okay, so on this one, example 1, it gives you the log, and then it shows you how it relates to exponents. But I'm going to write it on the side. I left the answers there, but I want you to remember that if you have, oops, I forgot to put my little pencil on there. There we go. Okay, so if you have log base 7 of x equal to y, I normally write it like the log part first rather than what they have backwards like on part A. Then when you go to write it in exponential form, remember it's kind of like this, okay? So 7 to the y power is equal to x. I know it looks a little confusing because it doesn't have numbers in there right now, or at least not enough of them, but that is the form of how you set it up. So like on part B, if you had log of 4, base 4 of x equal to some number y, then you write it like that. So you do like a little loop-de-loop. So 4 to the y power is equal to x. So on example 2, change each exponential statement to an equivalent statement involving a logarithm. So remember how we write it generally. We have this to there. It makes that little loop-de-loop. So we would put log base 1.6 of w is equal to 3. The little exponent goes on the outside. Same thing here. So when it's log base e though, we normally don't write log base e of 25 is equal to u. We write ln, the natural log. I would much prefer to see that. Don't leave log base e. Okay, and then this one, it would be log base b of 27 is equal to 5. That's how you would write it. All right, for example 3, change each logarithmic statement to an equivalent statement involving an exponent. So when we're going to write them, again, like that, okay? So b to the third power is equal to 8. Because it's ln, log base e, which I don't even know why they wrote that, e to the negative 2 equals c. It should be ln instead. Okay, and this one would be 4 to the w is equal to 6. So just make sure you know how to write it from log form to exponential and vice versa. Now we're going to work some more problems with it. Okay, so in this part, example 4, find the exact value of the logarithm. Okay, so this means don't use your calculator, guys. You don't need it. Okay, so remember we write it like this. So we have 3 to some power equal to 81. So just get them to have the same base. This would be 3 to the x, obviously. This is 3 to the, what is that, 4th? So that means x is 4. So if you can get the same base, do so. Again, this one, we write it around. Remember, this is like equal to y or x or whatever letter you want to call it. This would be 5 to some power is equal to 1 over 125. So rewrite it with the same base. See if we can get that to be a 5. We can. This would be what? 1 over 5 to the third. So that means we have 5 to the y equal to 5 to the negative 3. So I know y is negative 3. Okay, as far as the domain and range go, the domain of logarithm functions is equal to the range of the exponential, and the range of the log is the domain of the exponential. It's kind of vice versa. So let's look at how that's going to show up in a problem. Okay, so example 5, find the domain of each logarithmic function. So remember when you're looking at the domain restrictions, what you need to pay attention to is what's inside here. Okay, the part in here would have to be greater than 0. So we know, like on part A, x plus 2 is greater than 0. So I know x has got to be greater than negative 2. So this is answer to part A. Part B, same concept here. What's inside here would have to be greater than 0. You just got to remember how to work those that have the rational expressions. Let's see if you remember. Okay, greater than 0. Remember, we would like basically multiply both sides by 0. No, we don't even want to do that. We want to, we got to look at our critical numbers. Yes, that's what it is. Denominator and numerator equal to 0, and that's going to be our critical numbers. Okay, and that'll tell us, and then we got to check it because we don't really have an easy way to go about that because of the inequality. Okay, so x is -5 is one of my critical numbers, and x equal 5 is the other. So basically, I'm testing from -5 to 5 and seeing where does it fall. Like it's either going to be on either side or in the middle. So I'm going to just test x equal to 0. So if I put 0 in my original equation, I would get 5 over 5, so that's 1. 1 is greater than 0. That would be a yes. So I know the interval from -5 to 5 would be my domain, my solution set. And then on the last one, that probably is one of the easiest ones. This needs to be greater than 0. But if you're taking the absolute value of it, it's always going to be greater than 0. So it just can't be 0. So on part C, x, the absolute value of x has to be greater than 0. So the only thing, because x would be in between here, x is greater than 0, x is less than 0. So really the only thing we got to worry about is x can't be 0. So x is any number but 0 in that case. Okay, this slide just shows us more information about the properties of the exponential functions, the domain, the x-intercept, asymptotes, all that fun stuff. I'll let you read it. Okay, so this one is a graph, or graphs of exponential functions, and they're inverses, so you can see the log versus the actual exponential and how they look. Notice they are symmetric across the line y equal to x. They are inverses of each other. And this one has the graph of the natural log function. So notice the natural log is e to the x power. They have the natural log of x. They are inverses just like the others. They undo each other. They're symmetric across the line y equal to x, but that's what the graphs look like. Alrighty, so example 6, graphing a logarithmic function and its inverse. Find the domain of the logarithmic function of this. So remember, when we're looking at domain, we're concerned about what's in here. It has to be greater than 0, right? So all we have to do is say, well, I know x plus 1 has to be greater than 0. So that means x is greater than -1. So that's basically our domain. They want us to graph this. You can just use your graphing calculator and look what it looks like. Okay, I'm okay with that. From the graph, determine the range and the vertical asymptote. All right, so if you look at the range, once you graph it, and you could pause me here and then go graph it and see the picture and see what it looks like. But our range then is going to be all real numbers. And the vertical asymptote is at x equal -1. Find the inverse of f. Ooh, that should be fun. Okay, so if we find the inverse, that means we're taking the original function, which is up there. We're going to interchange the x and the y. So we have y equal to, let me see if I can squeeze this in, -ln of x plus 1. And I'm going to interchange my x and my y. All right, so let's see, got negative ln, so I need to divide by the -1, right? So negative x is equal to ln of y plus 1. If you remember working with ln, you need to do to the e on both sides, you know, the e power, so it's e. Actually, maybe I need to move that up so we have room, because I have a feeling I'm going to run out of room. Okay, so we have e to the negative x equal to y plus 1. So e to the negative x minus 1 is equal to y. So our inverse function would be e to the negative x minus 1. That wasn't so bad, if you remember how to work with the exponents. Okay, find the domain and range of the inverse. Let's see, our domain of the inverse is the same thing as our range of the original. So I know it's all real numbers. The range is the domain of the other one, which would then be y is greater than or equal to negative 1. You just have to remember, if you're not writing this in interval notation, that you're switching your x's and y's around. And then graph the inverse. You can use your calculator again on that and just look at a picture or a Desmos if you don't have a calculator with you. Okay, so this one is a picture of the common logarithm function and its inverse. So notice it looks almost exactly like the other one. They're so similar. All right, so example 7, find the domain of the logarithmic function. Again, we are concerned about this middle piece, okay? So that's got to be greater than 0. So I know x minus 2 has got to be greater than 0, so x has to be greater than 2. That would be our domain. Graph it, use your calculator again, our Desmos calculator, there you go. From the graph, determine range, vertical asymptote. So range, if you're looking at the picture, is all real numbers. I should have wrote the word range first, but that's okay. The vertical asymptote is x equal to 2. You'll notice very similar to the one we just did. Find the inverse of f. All right, so that means we're going to take that top equation. Again, you know what? I'm going to just start over here. We have y equal to 2 log of x minus 2. I'm going to interchange my x and y like that, and then solve for y. So this would give us x divided by 2, because we have to divide by 2 first. And then to get rid of the log, remember this is like I'm going to rewrite it in exponential notation here. This is base 10, so we have 10 to the x over 2 power equal to y minus 2. And we'll do more of these logs too in class. So this gives us 10 to the x over 2 power plus 2 equal to y. So my inverse function, let me see if I can write it right here, make it fit. This would be 10 to the x over 2 power plus 2. Perfect. All right. Find the domain and range. It's the flip-flop of the other. So the domain is going to be all real numbers. The range would be y is greater than 2. I'm just changing the values there. And then to graph the inverse, you can use your calculator, look at the picture, or Desmos, whatever your little heart desires. Take a look and see what the graph looks like. All right, now we're starting to get to the fun stuff, solving logarithmic equations. Okay, if you have an equation like this, one of the ways you can solve it is write it in exponential notation. Remember, this means 5 to the 3rd power is equal to that. That's what it means. So that would give us 125 is equal to 3x minus 4. So to solve that equation, I would add 4 to both sides, so 129 equal to 3x. And if you divide by 3, I believe you get 43. Y'all can double check it for me if you like. Okay, the next one, same thing. This would be x squared equal 81. So you take the square root of both sides. So x has to be 9. Now remember, it could be positive 9 or negative 9, but not here. It can't be negative because they're dealing with the logs. All right, so on example 9, solve e to the 3x power equal to 7. So if you have this, you're more than welcome to write it in exponential function, but I'm thinking the easiest thing here, let's just take the natural log of each side. Because remember, whenever you're dealing with these, you got the natural log. So if we take the natural log of each side, let me fix that. Okay, and remember, at this point, that's when the exponent can come down in the front. So this is 3x times ln e equal to ln 7. Remember, ln E is 1, so that's just this. So that means x would be ln 7 divided by 3. And if you plug that in your calculator, I think you get 0.649. You can double check that for me and let me know if you don't get the same thing. Kind of depends if they ask you for a decimal or the exact answer. The exact answer would be the first one, ln 7 divided by 3. The approximate one, decimal approximation, would be 0.649. All right, so alcohol and driving. This one looks like a fun one. Blood alcohol concentration is a measure of the amount of alcohol in a person's bloodstream. Reading of 0.4% means that a person has 4 parts of alcohol per 10,000 parts of blood in the body. Relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. For example, if an individual with a blood alcohol level or concentration of 0.02% is 1.4 times as likely to have a car accident as an individual who has not been drinking. Wow. The relative risk of an accident with a blood alcohol content of 0.02% is 1.4. Okay, so recent medical research suggests that the relative risk R of having an accident while driving a car can be modeled by this equation. X is the percent of concentration of alcohol in the bloodstream. K is a constant. All right, this is going to be an interesting problem. All right, so they want us to find K for part A. Golly gee, I'm going to need another page probably. You think I can fit it in here? Let's see. We're going to do all of these things, but I'm going to need another page. Let me see if I can figure out how to add a page. All right, I have added a page. You should be so proud of me. Okay, so let's find K. So if we want to find K, so this is part A, and they're asking us to find K. Since all the stuff's on the other screen, I'm having to slide over. We know 1.4 would be equal to E to the K times 0.02. Okay, so if we solve that, we would do ln on both sides. Remember, ln E is 1. That 0.02k can go down to the bottom. So ln of 1.4 equal to 0.02k. And k would be ln of 1.4 divided by 0.02. That would be k. So if you plug that in your calculator, I believe you get 16.82. All right. So B says, what does B say? Use this value of K. What's the relative risk if the concentration is 0.17%? All right, so we have R equal to E to the KX. R is equal to E to the, K is 16.82. X is going to be 0.17. Okay, so if you do the calculations with that in the calculator, I think you get 17.5% risk. You can double check it for me. Part C, using the same value of K, what blood alcohol concentration corresponds to a relative risk of 100? All right, let's see. So if we have 100 equal to E to the 16.82x power. All right, so I got to take ln of both sides again. So ln 100 is equal to 16.82x. So x is ln 100 divided by 16.82. And that is about 0.27. So that means our risk is about 27% risk. Okay, part D. If the law asserts that anyone with a relative risk of 4 or more should not have driving privileges, at what concentration of alcohol in the bloodstream should a driver be arrested and charged with a DUI, driving under the influence? All right, that's an interesting one. Let's see. They're saying 4 is the relative risk, so 4 is equal to e to the 16.82x. All right, so we solve that. Ln both sides. So ln 4 is equal to 16.82x. So ln 4 divided by 16.82 is equal to x. So if we plug that in our calculator, we get about 0.082, which is 8.2%. That's why they're talking about when they blow a 0.8, they can be arrested, you know, because that's too much. So that's where they're getting that number from. Oh, that's so cool. That's a cool problem. Wonderful. All right, so work on your Math Excel tomorrow. Well, we'll be back in school by then, hopefully, and that way you guys can work together.